Hi, I'm Josh McPherson,
I'm Gage Fulman.
and for our fluid dynamics design problem, we're going to be demonstrating the conservation of mass. So a good example of conservation of mass and what we made today is you can see that we have a pipe right here, and we have two inlet volumetric flow rates, which would be Q1 and Q2. We have one from the side and one from the top. And basically we're demonstrating that the inlet flow rate is going to equal the outlet flow rate.
To represent conservation of mass, we built this for our experiment. It has two inlet pipes and one outlet pipe and a controlled volume. We are going to fill the entire apparatus with water and release the bottom and let the water flow uniformly. This will demonstrate that the two inlet flow rates equals the outlet flow rate.
So when we perform this experiment, we're going to have this entire thing filled with water. We know that the equation for volumetric flow rate is Q equals area times velocity. We have the area of the openings of all three pipes, so they're the same. For velocity, we're going to be using velocity equals distance over time. We have the distances of these separately written down and recorded already. And for the time, we're basically, the point of the experiment is we're going to let the water drain, and we're going to record the time it takes from the water to go from here to here for our first time value for Q1 and Q2. And then for Q3, we're going to do the exact same thing. We're going to record the time it takes to go from here to the bottom right here for our calculations. Go. So for our data from the experiment, here we have the lengths of the pipes recorded. And so we did the experiment 3 separate times outside of the video that we showed. And we got an average inlet time value through those both tubes of 2.96 seconds. We also have the radius of the pipe, which is the same because we use the same pipe. And here we have the calculated area of that circle cross section. Now for the outlet recorded times, on those same 3 experiments that we did outside of the video, we ended up with an average time outlet of 2.16 seconds. So we can verify conservation of mass because we know that Q inlet equals Q outlet. So in our specific case, it's Q1 plus Q2 equals Q3. And we know that Q equals velocity times area, which also equals area times length over time, because velocity equals length over time, or distance over time. So we can set that up in this equation right here. We can plug all of these equations in for here. And if we plug our numbers in, we get a Q3 value, a volumetric flow rate of 2.398 times 10 to the negative 6 meters cubed per second. Now we can do it the other way to verify this by taking our Q3 equals length of outlet pipe over time outlet times area, which would just be the Q3 equation, which is right here. And we plug these numbers in, and we get a Q3 value of 2.003 times 10 to the negative 6 meters cubed per second for our volumetric flow rate. Now here we have our compared values from the Q1 plus Q2, and then just calculating our Q3, and they are pretty close. So we have proved that conservation of mass is real.